Hello and welcome to the next lecture. Last time we discussed filters and use of that filters in different applications, in different types of applications. We had common mode filters and differential filters, and for those we used capacitors and coils, and then we introduced ferrite beads. And we will now continue this story in a little bit more detail regarding the power supply filtering and especially bypassing. What does that mean, power supply bypassing? It means that you want to make very stable power supply voltage for all the circuits in the PCB. And that can be achieved by using a special technique called bypassing. Bypassing requires capacitors that are placed very carefully, and these capacitors then supply the stable voltage to all the circuits. And this doesn't just supply this stable voltage, it also affects the noise that is present on the power supply lines. And as you may already remember, the noise on the power supply lines is one of the noise sources of electromagnetic interferences. And although these power supply lines here do carry DC voltage and DC current, they also carry a lot of current, noisy current, that comes as a consequence of high-speed circuits that are supplied. And this noisy current then is transferred through the power supply lines via so-called common resistance paths. Paths that are, it's a conductive noise that conducts through the tracks on the PCB between different parts of the PCB. And in order to keep this noise local to the source of that noise, which in case of this picture here is the microcontroller, and this high-speed circuit here, in order to keep this noise close to the source, you can use two techniques: bypassing and decoupling. What is the difference? And today, in this lecture, we will talk mostly about bypassing. A bypassing means that you add a bypass capacitor, and this bypass capacitor supplies the current that is taken from the power supply by this noisy integrated circuit. And this capacitor then provides a so-called short high frequency path for this current. So you can imagine being this current as a current source that is transferring, or that is supplied by this power supply voltage. So we have a stable voltage here, we have a DC current flowing here, but the AC part of that current, the high frequency part of that current, is then supplied from this capacitor. This capacitor then actually provides a very short bypass for that current. That's why it's called bypassing capacitor. Decoupling. Decoupling means that you want to decouple that noise that still is present here. So most of the AC current comes from this bypassing capacitor, but there is some AC current that also is taken from the power supply because this capacitor is not ideal. Then you use filtering, a filter here, which you might already know. And that filter would then filter this noise away, and it would keep this very, very sensitive victim away from this noisy part. So here you would have only the DC current, here as well. So the voltage here would be also stable because the current would not be AC, and this AC current would be supplied then from this capacitor, and that coil and that capacitor will filter it so that it doesn't spread throughout the circuit. So this is called decoupling, because you are decoupling the noisy part away from the victim, from the sensitive part of the circuit. And this is called bypassing. And today Today we will mostly talk about bypassing. How to choose this capacitor, what type of capacitors are good for that, and so on. And we will split this into 2 separate lectures so that it wouldn't be too much at the same time. I hope that's fine with you. Alright, so let's start now with some real pictures. Here is an example of a digital circuit. It's a microcontroller of some kind, which contains millions and millions of transistors, which couldn't be even seen in this picture because they are too small. Now, these transistors are the cause of all the problems as well. As long as, of course, they are the, very, very useful part of this microcontroller, because without those transistors it wouldn't work at all, but they also cause problems. And what are these problems? Imagine a single MOSFET as a building block of the microcontroller. All microcontrollers are made in so-called CMOS technology nowadays. So CMOS means complementary MOS. And this means that they contain N-channel MOS and P-channel MOS transistors. And each MOS transistor has at least one major capacitance called the CGS, between the gate and the source. Of course, there are other capacitances. Actually, there are as many as the terminals altogether. And this capacitance has to be charged and discharged each time the MOS is turned on or off. And turning MOS transistor on and off means that you change the logic level. So each time you change the logic level, you are actually charging and discharging a small capacitor. And as the logic gate complexity increases, the number of capacitors increases as well. So what you have to remember from this picture is that you have many capacitors inside a digital circuit, and each time any part of that circuit changes logic level, you have to charge or discharge this capacitor. For example, if you have an inverter, it's the simplest CMOS circuit you can get. It contains one N and one P channel MOS transistor. And when you have logic 0 here, you have logic 1 there. So how do you achieve that logic 1? You have to open the upper P channel transistor and close the bottom one. And then by that, you're actually charging this capacitor. What is this capacitor representing? Actually, it represents the capacitance of everything that's connected to this output. The input capacitance of the next logic gate, output capacitance of that one, and so on. All the capacitance that they are there. So you have to charge these capacitances, and when you have the opposite, when you put logic 1 here, you have to make logic 0 there. So you discharge this capacitance. So charging and discharging the capacitance is all that digital circuits do all the time. I did a simulation of that a little bit. So I actually took a MOS transistor here, actually a inverting logic gate, N and P channel transistor. I drove it with a pulse signal, and I'm charging 100,000 capacitors of value of 10 femtofarads. So actually I am charging here 100 picofarad capacitor. I think it's 1 nanofarad. So I have 3.3 volts power supply voltage, and what do I get? Okay, I get this. So the blue is the output voltage. It drops to 0, we have logic 0, we have logic 1, logic 0, logic 1. It's all about charging now this capacitor through these 2 MOSFETs. And MOSFETs have a certain channel resistance. So therefore, that channel resistor is even not linear, it's non-linear. Therefore, this shape of the curves are somehow smooth, I would say. So each time you change logic 0 from logic 0 to 1, you actually need a current that flows from the power supply here. So current is flowing from the power supply to charge this capacitor. This is turning to logic 1, and turning to logic 0 means that you actually discharge this capacitor. So here you are charging the capacitor, here you are discharging, charging, and so on. So the power that flows from the power supply is the green one. That's the current that flows from the power supply. And it flows only when you change from 0 to 1. When you change from 1 to 0, it doesn't flow from power supply, it flows to the ground. So both currents are important. One flows from the power supply, the other flows to the ground. But that's not all of it. If I now go back to the previous picture, as you see, in the time between this transition occurs, also both transistors are open for a small period. So when the bottom transistor is, let's say, turning off and the top is turning on, there is a short period when both are partially turned on. And this is so-called crowbar current, the red one. Sorry, but that really annoys me. I don't know how to change that, but there is a problem with Microsoft. The crowbar current is the current that shoots through directly from power supply to ground. So each time that happens, there is a short period when you have a short circuit between power supply and ground, in addition to the charging and discharging. So here actually, that's why this current from the power supply is a little bit bigger than the current charging the capacitor itself, the red one. Now, how do we use that in a simple rule of thumb calculation? Well, actually you use a triangular signal instead of that smooth one. So triangular signal, that's a trapezoidal signal. That triangular is the wrong name. I have to change it actually. So I corrected it. So it's trapezoidal shape. Now this trapezoidal shape is then, fairly good approximation of the output voltage. So the charging of that capacitor then requires some constant current actually. So that current that flows through the power supply can be approximated as a square-like shape current. So maybe I can do that. Okay. So actually we can approximate this green as a square shape current with the value of the C times du over dt. Why is that so? The current through the capacitor is C du over dt, but if the voltage changes linearly, then it is equal to the delta U. It's the delta U is actually the power supply voltage divided by the time in which it changes from 0 to maximum. And actually that's what I did. So estimating this power supply current, if you take a linear transition from 0 to power supply voltage, the current would be square-like. It would be constant in this time. It's not exactly that, but that's the first approximation. And from that we can estimate what is the current spike that actually happens. And it's equal to this. Number of capacitor times the capacitance of a single capacitor and the UDD over delta T. So that's the equation you should be able to derive anytime. It's not requiring a lot of math. So if all logic gates would switch at once, you would get at least that current from the power supply. Of course, they do not switch all at once, and of course, they do not switch all at once from 0 to 1. So it is less, of course, in the reality. So let me show an example. Now, if we have 10 to 5 transistors, each gate capacitance of that value, power supply voltage is 3.3 volts, working clock is 100 mega, and for 100 mega we suppose that we can have this 10 nanoseconds at 100 megahertz divided into 3 parts: increasing part, flat part, and decreasing part. Okay, so at least 3 nanoseconds or similar, 3.3 nanoseconds would be enough for the rise time, I suppose. But, well, it could be even less. But let's say it is that. So 3.3 nanoseconds will be transition time. That would, of course, require 1 amp from the power supply. 1 amp is quite a lot. Now imagine that you want faster processor. 10 times faster would mean also 10 times the current. 10 amps from power supply. Okay. Now bypass capacitor. A basic approach would tell you, okay, my bypass capacitor has to supply all the charge during this small transition time. All the charge means that the minimum capacitance required for this capacitor would be in the range of the charge divided by the maximum voltage change, because that capacitor, which would provide the charge for this current spike, would then drop the voltage. So actually we can say that C is the charge taken from the capacitor divided by the maximum voltage change which we allow, and this voltage on this capacitor would then change by the small amount. This is the current that flows, and the current in a certain time would be the charge. So that's how we define the capacitance. And we say, let's say that, for example, for digital circuits, the maximum voltage drop allowed would be in the range of 100 millivolts. That would still allow the digital circuit to operate properly, but it may not be enough in terms of the noise on the power supply voltage, which could be even much less and should be even much less. But let's say we are now speaking barely about the operation of the microcontrollers. So estimating that, let me show an example. So we have a minimal bypass capacitor required. The maximum voltage fluctuation is here. The current spike is estimated to be in range of 1 amp. And putting all that in the equation would give you this range of capacitance. All right. So we are in range of few 10 nanofarads. For 1 amp, that's quite, low. I wouldn't pay much attention. I would just put a capacitor of 100 nano and I'm on the safe side, right? That's all what we do actually. What we actually do in our circuits, we put capacitors all around on the power supply and between the power supply and ground, just to make sure that voltage is stable at every point of our circuit. Now, how much of that capacitors? How many? What the capacitance? What type of capacitors? How to place them? These are all questions now that we should ask ourselves. And of course, the obvious answer would be 100 nano. We all put that and we don't ask. We just put them, and if it works, we don't care. 100 nano is like a golden standard for all the bypass capacitors. Of course, that's just in the wildest approximation. All right, so let's go now and try to do some simulations. All right, so I did a simulation and I put a power supply here. Let's say that our power supply has internal resistance of 1 ohm. That's also the resistance maybe of some copper wires around anywhere, and 33 nano capacitor and the pulse of 1 amp in 3.3 nanoseconds. So these are 1 amp pulses, the red ones, and each time the voltage drops for 100 millivolts. Then of course, since it has a resistor here, it would charge a little bit back and then drop again. Charge, drop, charge, drop. Doesn't seem to be really efficient, this 100 nano, right? It seems like that we forgot to take something into account. We forgot to take into account that the capacitor is not just for one single current spike. These spikes repeat all the time, so they have a certain frequency. And that capacitor also is connected to a power supply network, to a power source, which is connecting to this chip via some tracks on the PCB, and all that affects the operation of the power supply in general. So we have to use and apply the knowledge of our power supply circuit as well. So the power supply circuit, it contains some voltage source. Usually it's a switching mode or linear voltage regulator. And then in addition to that, it contains some tracks. And these tracks have certain inductance, resistance, and between the tracks and ground there is also some capacitance. So all of that is connecting the power to the load. Our load is the microcontroller or the integrated circuits that are there, all the transistors, everything that is supplied by this power supply. Now, this load is connected to this source, and that source together with everything here represent a certain impedance. And as you may know, the impedance of the sources should be low as possible. And I'm not talking about total impedance, so voltage divided by the current. That might be a little bit too much. So it's not voltage divided by the current, but the impedance of the source is the change of voltage divided by the change of current. It's so-called incremental impedance. And incremental impedance of an ideal voltage source should be 0. So regardless the current that is taken from the power supply, the voltage change should be 0 because our voltage supply is ideal. So the output voltage is constant. The voltage change is 0. Please keep that in mind because it is not very obvious. For some guys thought that we are talking about the impedance as a DC value. It's not. It's AC value. The voltage, and I couldn't stress that more, the output voltage should be constant. Therefore, the voltage change delta U should be 0. Therefore, the impedance should go to 0 as well. All right, I hope I was clear enough. So going back to this. How do we then define this impedance? What is enough impedance for our circuit that it provides good enough voltage source for our load? Well, I would say so. If you know what is the permitted voltage change, and if you know the size of the current spikes that are taken from the power supply, then you can define this maximum power supply impedance as this simple value. Delta U over delta I. And maximum allowed power supply impedance for our case, for example, would be in the range of 100 milliohms. Why? Well, the voltage ripple we are allowing is in range of 100 millivolts and the current is 1 amp. So the impedance is 100 milliohms. This is what we have. So the next question is, how do we achieve that? Well, there are two main parameters defining the impedance of our source. The voltage source itself and the tracks. And the voltage source is usually a voltage stabilizer or a regulator. Or it has some sort of a stabilization network inside the chip which has a frequency limited operation. And on the other side we have copper tracks that are taking the voltage from the source to the load. And this track has usually prevalent inductive load and inductive nature. Inductive nature at low and medium frequencies, and at very high frequency, I'm talking about hundreds of megahertz, the capacitive nature also comes into play, but only then. Let's check now first the voltage regulators. Usual linear voltage regulators now are made of a reference. This is a reference voltage. Then you have some sort of a transistor that defines the output voltage. It's a regulating element. And then you have a feedback consisting of some resistors and a feedback amplifier. It's error amplifier. So this error amplifier is not the fastest there are. So what that means is that if the DC current is taken from, or low frequency current is taken from the power supply, the regulator can follow the changes in this current and can control this transistor in real time. But when the frequency of the current increases, then this does not follow. It stays behind. It lags. And that lagging of that amplifier can cause us the lagging of the voltage here. So the voltage starts to change, and that increases the impedance. If you plot the impedance, the output impedance of this regulator, you will get this. The output impedance increases in this manner. We have a log plot here and log plot here. So this would be a line in log plot. What does it look like? It looks like you have a coil. And if you take the same circuit and do the AC analysis of the impedance of that coil of 10 microhenries, you would get the same picture. So that voltage regulator acts as a coil, as an inductance of 10 microhenries, which is a lot. So which means that at frequency our microcontroller is operating, this impedance would be in the range of 10 and more ohms, which is a lot. So change of 1 amp would change voltage in the range of 10 volts, or that's really a lot. So it's not just that. This is just one part, the voltage regulator part. And the other part is the copper track impedance. And now, how much is that? So first of all, there is a certain resistance here. And then the inducting nature starts to prevail. So you have a coil again, or let's say something like that, with a certain resistance. So this is the impedance equivalent circuit for the copper track on the PCB. And that actually, how much is that coil here? So we have R and we have omega L here. So if you check out the values here, at 10 megahertz, you get around 2 something ohms. So the impedance, which would be the R plus J omega L, at 10 megahertz, as you may see here, the resistance is less than 100 milliohms. The omega L would be in the range of 2 ohms, so it's more or less equal to the omega L. So if it is around 2 ohms and omega is 2 pi 10 megahertz times L, then the L can be easily calculated. L would be in range of 2 over 6 times 10 mega, so it's 1/30 of the microhenry. So it would be in the range of 30 nanohenries. 30 nanohenries is a single track. How long? 3 centimeters long and 0.5 millimeter wide on the PCB. So we can say that each millimeter of track on the PCB would correspond to 1 nanohenry. That is something you could remember, because that is quite easy to remember and it's very useful to know. Now, how much is that? Well, it's much less than the voltage regulator problem, because with that one we are talking about microhenries and here is nano. At least that. But if we used wider track, then the impedance would be less. So you would go down. Okay. So how much? If you take 5 centimeter wide copper plane, then this finite copper plane, of course, would have at least, I think, in the range of 100 times less impedance. So I'm talking about maybe 0.3 nanohenries instead of 30. And if you have infinite copper plane, which is this line here, it would be even 10 times less. So it makes sense to have wide planes to supply power supply to all parts of the circuit. But still, you cannot be, you can do that if you have several layers available. If you have only 2, then you are quite limited. So let us go now into a little bit into a detailed analysis of the power supply circuits. And I will start with this example. So what do we have? We have power supply line. Let's say for a start that we have ideal voltage source. So we do not include this impedance of the voltage regulator. We just include the impedance of the tracks. And let's say we have a 10 centimeter track. A 10 centimeter track would give you around 100 nanohenries and a few milliohms of resistance, of course. Depends on the width or the thickness of the copper and so on. And of course you have to return back somehow. So this is the impedance of the forward and return line on the power supply. And this is the load. That's our integrated circuit. And I'm measuring the impedance of my source. And impedance, of course, at low frequencies is determined mainly by the resistance of the wires, of the tracks. And then this omega L part prevails. And the omega L part then increases. And of course, the impedance, which should be below 100 milliohms, is now quite easily exceeded. And if I go into simulations now, you would see that this impedance at 100 megahertz, which instead being 100 milliohms, it's in the range of 100 ohms, would be causing a lot of problems. Taking 1 amp current from power supply would actually even not be possible. So actually I'm making here a little bit harder. I make it as a resistive load. And here you see that the voltage changes from 0 to 50 ohms and more, because the current spike that is taken from the power supply would drop voltage immediately to 0, and when the current stops flowing, the voltage built on this coil would just continue running the current, because the coil wants to run the current or wants to keep the current constant. Therefore the voltage would turn around and it would cause a voltage spike of range of 50 volts and more. And that behavior of coil is very well used in petrol engine cars when they are generating sparks for the spark gaps to ignite the engine. And yeah, there the coils are very useful. Here we don't need them, we don't want them, but they are there in every circuit. So this is totally useless if you have a voltage power supply and 10 centimeter track and the microcontroller taking 1 amp from the power supply. It would be disastrous. So we need to do something. And the question is how we do that. And here the answer would be the following. I will actually show it here in a drawing. So what do we have? We have a source. We have that source with a coil. So this is a inductance of power supply lines. And here we put a capacitor. So that would be our so-called bypass capacitor. Now, what does it do? If you look closely from the side of our load, if you look in that direction, I will actually draw load a little bit further away so that I could draw that. If you look from that direction, that load sees these two components as being connected in parallel. So actually, we have a parallel connected LC circuit. How do we draw an impedance of such a circuit? Well, this is omega and this is Z. At low frequencies, the impedance of coil is 0. So that means only the resistance stays. So I will put a small resistance here. So it is 0, or it is equal to air power supply. Then the coil prevails. So we have a coil. This coil increases with omega L, power supply. And then we put capacitor. The impedance of capacitor is 1 over omega c, right, with yacht. So it goes down 1 over omega c. Here we have a resonance. So we should put, if I draw now the minimum impedance, the maximum impedance we want to achieve, not more, then we have to move this omega c in such a way that it would at least go to this point here. And then the question is, how much is the capacitance? Okay, let us look. The capacitance is 1 over omega c. The resonance here is called parallel resonance, omega parallel. So let us now draw a few, write a few equations. The omega L power supply in this point is equal to Z max, right? And it's equal to 1 over omega C. Okay? This capacitor. This is a bypass capacitor. So, if I continue now, I can say, okay, let me see how much the omega is. The omega is, from these two equations, is 1 over Z max C. Or it is also even from these two equations, the omega is Z max over L power supply. Okay, so I want to know how much the C is. So I will derive the C out of it. The C is equal to 1 over omega Z max. Omega is equal to 1 Z max over LP. So the final equation is LP over Z max squared. L power supply over Z max squared will give you the capacitance C, and the omega, this parallel omega, would be equal to 1 over square root of L power supply C. All right, so now I have this parallel resonance frequency, and we have the capacitance. So now, is it solved? Is that what we wanted? Well, the impedance very away from this parallel resonance is well defined. Here and here. But what about in the resonance? The parallel circuit, resonance circuit, in its resonance frequency has infinite impedance. So the impedance actually would go up like that. And that depends on the quality of this resonance circuit. The lowest quality, the better. The highest, the worse. Because we could achieve low impedance at all frequencies except at parallel resonance. Doesn't matter what we do. We have this spike here if we use this capacitor. And please remember, all the time, anywhere you look, you have resonance circuit. A capacitor which would connect somewhere would again feel or have some parasitic inductance which would then make it a resonance circuit. And the coil has the same. All that means that anytime, everywhere you use a component, it is always a LC resonance circuit in some sense. Depends on the frequency range. And this is what you have to keep in mind. Because here I put this capacitor, I didn't solve the problem completely. Let me show you this example here. This effect of bypass capacitor, I just put here 100 nano capacitor. I told you before, we put 100 nano capacitors everywhere, so why shouldn't we put it here? Well, actually, this 100 nano capacitor has a frequency at which it crosses this maximum impedance, 100 milliohms here. So it's not adequate. But that's not the point here. The point is that we see a very, very sharp parallel resonance. And this parallel resonance, which consists of a power supply line, in a coil or inductance, and the capacitance of the capacitor, now makes us a lot of problems, because here in this range the impedance is not sufficiently low. And actually, if I do a transient simulation of that, you see that each spike that is generated by this load would actually decrease the voltage further. It wouldn't have time to charge. And if you do that quite for a long time, you get actually some oscillations like that. So this is in 20 microseconds. So each point here corresponds to a single 10 nanosecond pulse. Now, if I do that again, if I make one pulse here, wait for a long, and then make another one, I would get this. Even though my frequency of the pulses that are taken from the power supply is very, very low, this is frequency in the range of 20 kilohertz, you still see a lot of oscillations, because our circuit is undamped LC resonant circuit. And that's not all. The capacitor I put here is an ideal capacitor, the best there is, the best in the world. And it's not adequate. How can we do it even worse then? I mean, every capacitor you take would be worse, right? So let me show you a real capacitor. This is a real capacitor. A realistic capacitor has at least two additional parameters: a series resistance and series inductance. And if I show you the capacitor, it would be something like that. The capacitor is a series resonance circuit. That series resonance circuit then has this. The series resonance circuit is actually this. And at low frequencies, it has high impedance, because the capacitor is 1 over iota omega c. It has high impedance and it decreases. This is 1 over iota omega c. And then at a certain frequency, the coil starts to prevail. So this is the omega L. So here is the resonance. The resonance would be series resonance, and is calculated as 1 over square root of LC again. L series in this case. Now, this is what I show you here in this slide. In this slide, you see the impedance of this capacitor changing in time with frequency. At low frequencies, you see the capacitive nature. Here you see the inductive nature. And if I now increase the capacitance, what will happen? If I now increase the capacitance, the impedance at low frequency, would decrease. So high capacitance means this is low capacitance, here is high capacitance, means low impedance at low frequencies. Resonance also changes. But if I don't change the series inductance, this part is omega L series, it changes, it stays the same. Okay, I will now continue. Okay, what about the series inductance? If I change the series inductance, then my impedance at high frequency would increase. So increasing the series inductance would increase this part here. And the series resistance would change the quality of my resonance circuit, changing the series resistance. Increasing it would also increase this part. So I'm putting now a real capacitor in my circuit. That's a real capacitor. So what do I get? Instead of having very low impedance at high frequencies, it now introduces additional series resonance. And this series resonance is good because there I have very, very low impedance, but then you have inductive nature of this capacitor, which increases again. And that's really, really, really bad, because now I have again problems at high frequencies. My real capacitor now does that. This is at 100 megahertz, the pulses long 3.3 nanoseconds at 100 megahertz. And the voltage, the red one, changes from 2.5 up to 5 volts. It's not enough. So let us do another thing. Maybe I have a smaller capacitor of 1 nano, let's say, that has really, really low series inductance. So I add it in parallel. So I have a larger capacitor which has a little bit worse parasitic components, and there is a really, really the best capacitor there is, which has lower inductances, lower resistances, and so on. So I'm adding this one in parallel. Adding additional capacitor in parallel makes things even worse. Let me try to show that on this sketch. So actually what I did, now I will try to demonstrate it here. So, okay, this is a graph, frequency, impedance. And now I am having this. I have the series power supply inductance with one capacitor and another in parallel. All that is in parallel. C1 and C2. This one is worse, this one is better. So what I do have, I have low impedance at low frequencies. Then it increases with frequency. This is omega L power supply. Then I will draw it in red. I have the first capacitor. This is 1 over omega C1. Then I have the series inductance of this first capacitor is omega L series 1. Then I put another capacitor which has lower capacitance, therefore it has higher impedance. This is 1 over omega C2. And then this capacitor also has some omega L series 2. The values are chosen in the way that actually are following one after another. So the final verdict would be that blue curve here. So that would be the impedance of our circuit. Sorry. The first resonance, the second resonance, the third resonance, the fourth resonance, and so on. So this is the first parallel resonance, this is the first series resonance, the second parallel, and the second series resonance. And a lot of problems. So that's the picture. And the second capacitor was chosen so unwisely, or so, unfortunate, that the resonance actually corresponded to the 100 megahertz frequency, which means that it even had less impedance there, more impedance there. It was less quality power supply circuit. And it would be better not to put it because of this second parallel resonance. And that's the result. At 100 mega now this oscillates like a swing. So how to decrease the impedance at high frequencies? not putting another capacitor of much lower value, but maybe putting more capacitors of the same value. Because if you put more capacitors of the same value, what you actually get, connecting in parallel capacitors would increase their capacitance by the factor of n. N means number of capacitors. And it would decrease the series inductance and series resistance by the same factor. So actually, if I try now to show it here, it would be very, very quick and easy. What actually means is if I put n capacitors in parallel, then the capacitance would increase, n times c. The series inductance would decrease and the series resistance would decrease as well by factor of n. And that's important now to remember. Now, if I put all that, I actually get this. I now put 10 of these capacitors in parallel. So I got 1 microfarad of equivalent capacitance, but 10 times lower series inductance and series resistance. So my impedance is now lower in the whole high frequency range. Cool. Well, we still have a problem, don't we? We have a problem here. Here. So, what does it mean? If I now do a simulation at 100 megahertz, I actually get voltage change of around 100 millivolts plus minus, which is what I actually sort of wanted to have. It's not ideal, but it's there. What about if I change the frequency to 15 megahertz? What do I have at 15 megahertz? I have roughly the minimum impedance of 10 milliohms. So at 15 megahertz, my voltage change is very low, between 3.28 and 3.30 something. So it's very low. Cool. I'm working perfectly with this series resonance here. But if I change that to 500 kilohertz, well, I'm back in the old business here at the parallel resonance where the impedance is large. Around 500 megahertz is here. So 500 kilohertz. And I have nice swing, which changes my voltage a lot, and I don't want it. I really don't like it. Even if I go lower, if I have really, really rare spikes, I would actually get this. I have nice resonance circuit with large quality, so it oscillates a long time before it damps. Damping of that circuit is very essential. And remember, we already did damping of the LC filter, right? The LC filter was damped in different ways. And damping of that filter included using some resistors which can dissipate power. Like here, this resistor here, or that one, or so on. And regarding the power supply lines, we have a few problems. So we have power that is dissipated on the series resistor. We don't want it, so this is not an option. Here the impedance of the coil is very low. Well, if you put a resistor in parallel, it will not work at high frequencies as a voltage divider, so no way. Here, adding resistor in series with capacitor, again not a issue, not useful, because then you increase this impedance here, which should be very low. So again, and this one, again, high power dissipation. So what to do? Well, what you can do, you can actually use this damping here. This is the damping of the resonance circuit with using R and C. Cool. You can do that. And you already know that this damping resistor should be somewhere between two values, and the capacitor should be at least 16 times larger. Cool. If I put that in my simulation, I get this. I calculated the value of the damping capacitor to be around 20, and the resistor between these two values. Actually, it turned out that because of the in the simulation, the 100 milliohm resistor was just perfect, because here it defined the resistance of 100 milliohms of my impedance. So now the final result is that one. Using a damping capacitor of large value enough and just the right series resistance, and the bypass capacitor of a few of the same value and type. Let's say 10 of capacitors of 100 nano would give you the correct value. So why wouldn't I use one microcapacitor? Why wouldn't I use a capacitor of 1 microfarad with the series inductance of 0.1 nanohenry? Because I can't find such a capacitor. There is none on the market with such a low inductance, and I wouldn't be able to connect it. Please remember, if I put a capacitor and I connect it to something, I need wires, and 1 millimeter is equal to 1 nanohenry. So I cannot, even if I have such a capacitor, I cannot connect it, because every track that I will use to connect it would give me more inductance that I need. Therefore, I need several of them. And several of these capacitors can be placed if my integrated circuit has several power supply connection lines, power supply pins. Okay, the final solution at 100 megahertz is shown here. And if I now use a 50 kilohertz signal, you see that it is also quite well damped. So the noise is very well controlled. So let me finish this lecture, or this part of the lecture, with the final slide, with that one. What is shown here? Actually, I use the bypass capacitor to have a stable voltage here. But please note that usually what we do have, we have a voltage source here. And I shown before that the voltage source is usually a voltage source that has a very bad or not very good stabilization. So its impedance also has an inductive nature, and that inductance is in range of tens of microhenries maybe. Now all that we did not take it into account, but this can be quite easily solved by using a very large so-called bulk capacitor. Bulk capacitor is the capacitor which you put close to the voltage source you have, or let's say if you have a sub-circuit, you put it at the beginning of your sub-circuit which you're powering with this voltage source. And that capacitor would then act, because the value should be large, in the range of hundreds of microfarads, it would already act very closely to very, very low frequencies here. And then from that on, you would have wire. So this would be then the impedance of your, let's say, of your voltage source. And in the frequency range, I will now show here, it's not very well done, but let's say these are two tracks that are taking this voltage to your circuit. So these are then representing this inductance of the tracks, and the voltage source is now quite good, that voltage source here. So from now on, we have our bypass circuits. So to finish, I can say the following. The choosing of bypass capacitors is essential for your circuit, even to operate properly. And the next thing, the value of these capacitors and how you place it would then not just enable your circuit to work, it will also minimize the noise spread through these power supply lines, power supply tracks over the whole PCB. And the bulk capacitor, which you put it at the beginning when the power enters into your circuit, is essential to keep the impedance of your basic voltage source very low. And it will then provide a stable power source for the whole circuit you're powering. So if you have a lot of the individual integrated circuits then powered, you put one bulk capacitor and then you put several smaller bypass capacitor next to each one of these circuits. And the other thing is, the bulk capacitor, because it is very large, it's not very good quality capacitor, but doesn't matter because it has to act at low frequencies. And if it's not very good, then it might also be good for filter damping, because the series resistance would be maybe just the right one. And with that, I would like to conclude, because what I wanted to say is having a bad capacitor in your design is quite beneficial, because it would also provide the resonance damping, especially the parallel resonance damping, which would be your pain. Because imagine that you are not aware of that phenomena, and you are producing a device that goes into market, and actually it works fine. But after a year or two of your production, you plan, let's say, some changes, and you change the provider of one capacitor that doesn't make it anymore, or whatever it makes, you use the one which is cheaper, and so on. And this new capacitor you apply has different properties. Maybe they are better. Maybe that new capacitor has lower series resistance. Maybe it's superior in any sense, in any way, but then you have problems. Then if you apply this new capacitor, would have better quality, your resonance would shift a little bit further or lower, whatever. It would be more sharp. Maybe you would just hit the one of the noise and match it, and then noise sources in your circuit, and then you would have an EMC issue. And now imagine you are producing millions of these circuits, and they go into, let's say, cars. And now again, at a certain point, all these cars have problems with the EMC. Can you imagine how this designer would feel like when he got the request for the complaint from the company that buys the circuits from him? I mean, that would be a really devastating for the whole company. So this is one of the reasons maybe to make sure that anything you change, should be very careful to check whether this affects your design. So at the end, what are you supposed to learn after this lecture? You should be able to estimate some roughly estimation of the maximal power supply impedance according to a given circuit. So calculate the impedance required for that circuit. You should be able to sketch the impedance, how it changes with frequency if you use power supply bypassing techniques, capacitors, coils. You should be able to calculate series and parallel resonances of the inductors or capacitors, or different capacitor bypass arrangements. You should also be able to calculate appropriate number of capacitors for a given situation. And we will do a little bit of that as well during the consultation. And this is some of the literature you might be wanting to read. And these books, as you know, are all available. So I would like to thank you here and finish this first part of the power supply bypassing lecture. And see you soon.